Good morning, students. Welcome to another video of digital logic design. So today we are going to discuss about a sequential circuit for counting the sequence of any random numbers. Okay. So the question is design a sequential circuit for counting a sequence like 4, 3, 2, 6, 7 using JK flip-flop. Or you can say that the question may be asked like this. Uh, Design a synchronous counter which can count in the order 4, 3, 2, 6, 7 using JK flip-flop or T flip-flop. So when we attempt this question, first we need to find out how many flip-flops we want. So here you can see that the maximum digit is 7. So the maximum digit is 7, that means if we will take 3 number of flip-flops, so we can count up to 2 to the power 3 minus 1, that is up to 7 we can count. So here we need total 7 number of flip-flops. So here I have taken total, so we have taken n equal to 3, that means total number of flip-flops required 3. It can count up to 7. And you can see here the flip-flop, the counting sequence are not in the proper order, not in the ascending order or not in the descending order. It is in a random order, or that's why you can say that it is a random sequence generator. Okay. So to attempt this type of question, first we need to find out how many number of flip-flops required and which type of flip-flop required. You can see here I'm using here JK flip-flop. So in JK flip-flop, first to write down the excitation table. So first I wrote down the excitation table. So in excitation table, your input equal to Qn and Qn plus 1, your output equal to J and K. So we wrote the four possible combinations 0, 0, 0, 1, 1, 0 and 1, 1. So 0, 0, 0, 1, 1, 0 and 1, 1. For that, I will get 0 don't care, 1 don't care 1 and don't care 0. So once we wrote the excitation table, then we'll go for to draw the state diagram. So you can see here it is given properly. So when I'm trying to write, so I'm writing 4, 3, 2, 6, 7. So here 4, 3, 2, 6, 7 is the order. So first it will count from 4 to 3, then 3 to 2, then 2 to 6, then 6 to 7. Again, once it reaches 7, it will again come back to 4. So here what are the states I am not using? That is 0, 1, 5. These are the three states I am not using. So whatever diagram, whatever the, so I need to draw the state diagram. So I drawn the state diagram here. So this is 4, 1, 0, 0, 4. This is 3. This is, so 11, 4, 3, 2, 6, 7. And I can see the arrow mark. So the arrow mark indicates in the flow of this counting sequence. So now I can take any one is the present output. So you can see that this is the, I can write down, this is the present output I can write down. So this is the present state or present output. Okay, so I'm using here three flip-flops. So the three flip-flops are A, B, C and their outputs will be QA, QB, QC. So if QA, QB, QC is the present state, then QA star, QB star and QC star is the next state. So this is the next state. So I'll write down this is the next state. So QA, QB, QC is the present state. QA star, QB star, QC star is the next state. If I will take this is the present state, so I can say that this is the next state. And this is comes in a loop. So if you take anyone in the present state, so after this arrow mark, that is going to be the next state. So once the state diagram is over, then you need to write down the table. So the truth table for the conversion. So here I told whatever I told. So QA, QB, QC is the present state, and so this is the present state, and this is the next state. Okay. So once I wrote the present state, I told we're using three number of flip-flops. So I write down the possible combinations. We'll start from 0, 0, 0 to 1, 1, 1. So basically this is decimal value 0, 1, 2, 3, 4, 5, 6 and 7. So this these things I wrote. These are the present state value. Now from the state diagram, we will see what is the next state. So you can see here, as I told, 0, 1, 0, 0, 1, 5, we are not using. 0, 1, 5 is not using. So if 0 is the present state, or 1 is the present state, or 5 is the next state, so what is the next state we do not know. So what is the next state we do not know, so we'll write down the don't care. So you can see here, so present state is 0, so next state we do not know, so you put don't care, don't care, don't care. Similarly, 1 is the present state, so next state also do not know, we'll write down don't care, don't care, don't care. Similarly, if present state is 5, for that the next state also I do not know, I write down don't care, and don't care. Now whatever states know, 2, 3, 4, 6, 7. Now I will come here. If present state is 2, so the next state is 6. So 0, 1, 0 represents the present state. So next state is 1, 1, 0 represents 6. Then if present state is 3, so the next state, you can see the next state is 2. So the next state is 2. Similarly for 4, the next state is 3. Similarly for 6, the next state is 7. For 6, the next state is 7. You can see here. So for 7, the next state is, if present state is 7, so the next state is, if present state is 7, so next state is, you can see from diagram, so next state is 4. So I wrote here 4. So once I wrote the present state and next state, then as I am using 3 different flip-flops, and the flip-flops are JK flip-flop, so the input will be JK, JB, KB and JC, KC. So from this present state and next state, we can find out using the excitation table what is the JK value, JB, KB value and JC, KC value. So I'll take this one. So you can see here, I'm using first QA. QA is the output for the A flip-flop. So if QA is this and QA star is this, so I'll get here JK. You can see here present state 0, next state don't care, so I'll get don't care, don't care. Here also same thing, present state 0, next state don't care, so I'll get don't care, don't care. Same thing here, I'll get present state 0, present state 1, next state 1, I'll get don't care, don't care. Same thing I'll get for all the flip-flops. Now you can see here, so present state is 0, 1 minute, present state is 0, next state is 1. So from the diagram you can see present state is 0, next state is 1, so I'll get 1 don't care, so I wrote here 1 don't care. Similarly present state 0, next state 0, I'll get 0 don't care. So all these things we can get from the excitation table for JK flip-flop. So once for the flip-flop A over, so once this is over flip-flop A, so once it is over for flip-flop A, this is flip-flop A. Similarly I can write down for flip-flop B and flip-flop C. Okay, similarly you can write down for flip-flop A and flip-flop B. So next we will take QB the present state, QB star is the next state, and for that we can write down JB, KB. Similarly by taking help of this thing, so I'll write down for QC, I'll write down for QC and QC star, I can write down for JC and KC. Okay, so here I got J, K, JB, KB, JC, KC are the 6 outputs. Remember I'm getting here 6 outputs. So these are basically outputs, and QA, QB, QC is the input. Now for 6 outputs I can draw 6 K maps to find out. So first I will take in this J, and the input will be QA, QB, QC. So input will be QA, QB, QC, and I wrote the K map, and after pairing I will get J equal to QC bar. Similarly I can take K also by taking K and proper pairing I got K equal to QB bar. Similarly, I have taken here for JB. So for JB output I have taken, for KB I have taken. So JB and KB. By solving K map, I got some relationship. Similarly, for JC, KC, I got the relationship. Once you got the relationship, then you need to draw the logic or the circuit. So I told I have using three JK flip flops. So I'll write down like this. So let this is the first flip flop. The input equal to J. This is K. So output will get QA and QA bar. Next JB. Here KB, this is QB bar. Next JC, KC. Here I got QC and QC bar, right? So now I'll see. So JC equal to QA. So I'll write down JC equal to. I'll connect here JC equal to QA. So JC equal to QA connected like this. Then KC equal to 1. So I can connect KC equal to 1. Now JB equal to 1. So I'll connect like this. JB equal to 1. KB equal to QA into QC. So KB equal to QA and QC. So I'll take two outputs from here, QA, and I'll take from here. So connected to a AND gate that will be connected to KB. So this is your QA, this is QC. So KB equal to QA into QC. Next, J equal to QC bar. So here I got QC, so I'll take a different color here. So let me take the blue one. So I have taken from here. So I'm connected to JA equal to QC bar, right? J equal to QC bar. This will be QC bar. Next, your K equal to QB bar. So here I have taken Ka equal to QB bar. So this will be QB bar. Okay, as it is a synchronous counter, so we need to put a clock. That clock will be common to all. Let me take a different color here. Let it be like this. So a common clock I will take here. This is the common clock connected here. So common clock. Okay. So this is the clock and this is the circuit. So all are JK flip flops I have taken. So here if I am taking the output across QA, QB and QC. So this whole together will give the order, the output order like 4 3 2 6 7, then again back to 4. Okay, I hope you understood this numerical. If you have any doubt, you can write in the comment section. And if you think that this video is useful to you, then you can share with your friends, those who need it. Thank you for